Hello everyone, so this is my post-lab video reflection of flame test. So I went over the fire safety by doing two things, by having a bucket of water right next to me and my fire extinguisher right here. Then to ensure that the chemicals and lab equipments are not contaminated, I started looking at the chemicals and how clear the solution is. So if there were any impurities, I would assume that the solution was contaminated. So I checked all 4 bottles. Then for the inoculating loop, what I did was that I took a piece of clean paper, a clean towel, and I used that to wipe it off. So other than this two, I didn't think of anything else that would be considered as contaminated chemical or lab equipment or in terms of fire safety. Now, while doing the experiment, I did take a video, although since my light is right above me, the color of the lithium and sodium chloride, they were not that very clear, but I could still see them, plus my camera was not up to the mark. So let's go to the results section. So when I was doing lithium, when I was doing flame test for lithium, lithium had there you go. Okay, so lithium took about 10 seconds to heat up. The solution was clear. The color was like pinkish red, mostly towards red, but I could see slight hint of pink. That could be due to the halogen light interfering. So based on the tabular chart, the wavelength was of 650 to 700 nanometers, and electronic configuration of lithium is 1s2, 2s1. So in terms of sodium chloride, again the solution was clear. It was a bit faster than lithium in terms of heating up. The color was orange, sort of brightish orange, and the wavelength from the table was 595 to 650 nanometers, and electronic configuration was of 1s2, there's 2 electrons in first shell, 2s2, 2p6, and 3s1. Potassium chloride was slower to burn, but solution was clear. The color was violet. Wavelength was 400 to 435 nanometers, and electronic configuration is too large. These are the electronic configuration of the ground state. I wasn't sure whether whether we want to put the electronic configuration of excited state after the heating of process. That is partly because I didn't do that because I think the lab, the table 3 does not specify whether the electronic configuration are supposed to be of a ground state element or an excited state element. So I would leave that, I would consider it as a ground state element, and I'm giving the electronic configuration of ground state element. Now for calcium chloride, again the solution was clear. It took about 11 seconds to heat it up. The color was yellow red. It was about the wavelength should be in about 580 to 600 range. Since the table did not had a yellow red perfect wavelength, I just guessed, I just pushed the yellow's limit from 595 to a bit higher. And the electronic configuration of a calcium at the ground state is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. So this would conclude the results for my today's experiment. Now, so turning to the self-reflection part, I'm just gonna look here and talk about it. So honestly, I looked at the SDS sheets that I found here for each element, and I used these SDS sheets just to make sure that, you know, I don't do anything bad while doing the experiment or burn up my house. So that was one thing that I was mostly concerned of. Other than that, the lab equipment, the lab manual was fairly straightforward. Although I would say certain part and certain elements of lab procedure could have been more clearer. For instance, when they say inoculating loop, they could have just shown a picture of inoculating loop, because it took a while for me to figure out that, okay, this is called inoculating loop. And they could have put some more pictures on each procedures, so that would ensure the safety of I think us, the students, and it will be less likely for us to make mistakes. Okay, continuing on from the critical thinking prompt, I'm choosing the first question. So as we heat up the elements, the fire is adding energy to the elements. So what happens is that elements in its ground state is stable, but when energy is given to the element, this energy is absorbed by the electrons, and these electrons then move from the ground state to the excited state. That is, they jump from shells, electron shells, from K shell to L shell, L shell to M shell, M shell to N shell. So because of this jump, what's happening is they are absorbing the energy. Now every element has to go back to its stable state. That is, all electrons has to return to its ground state. So what would happen is, when electrons are returning to the ground state, what happens is they lose energy, and this energy is released in like a discrete package of energy. Now this discrete packet of energy is the result that we see is the change in the color. So there would be a quick thinking here would be that, okay, so there's a change in the color, but why different colors? So different color is due to the fact that this electrons has to travel different distance to reach the ground state. So let's say if an electron jump from the K shell to all the way to O shell. Now he has to go down like 5 different shell levels to reach back to the K to his original K shell. Now this amount of distance traveled is what determines the difference in the color. So that is the difference in the wavelength. So hence this wavelength difference are the result of the different color. Quick note, I'll be putting 2 videos. The second video on YouTube would be like a 20-second video of showing the change in the color of lithium. Other than that, this concludes my video reflection. Everybody have a nice day. Saleh Al-Mari over and out.